Thank you, sir. Yeah, so I'll share. Can I share now? Okay. Can you see my sharing? Okay. So I'll try to see the slideshow. strong molecule. Very strong molecule. If you are familiar with this basic chemistry, you can see that this is a dinitrogen molecule, molecular orbital of dinitrogen molecule. Look at the calories that need to be that needs to break the nitrogen triple bond. You can see here N triple bond N. You need 473 kilojoules. That is a huge amount of energy. So even though we have 78% of the nitrogen in the atmosphere, but it is mostly useless. It is as good as a noble gas, which we call it as an inert gas. So fixing the nitrogen problem will be one of the major achievements that could be done. You might have heard about the Haber-Bosch process, which actually fixes the nitrogen, atmosphere nitrogen, combines with the hydrogen to form the ammonia. That eventually won the Nobel Prize for its remarkable invention from the Haber and Bosch. That is one of the reasons. One of the criteria how to fix the nitrogen. But what is the problem with Haber-Bosch process is that it uses high energy. Economically, it's not viable because the breakage actually takes breaking the nitrogen bond takes a high temperature, that's around 500 degrees centigrade, and also around 300 atmosphere pressure. So this is a very bulky, very expensive protocol. So there is another option that we can do is that what we can do is that we actually mimic the nitrogen fixation by using the plants. The plants actually do the same thing what Haber-Bosch process does by just in the room temperature, and then they break without any pressure. So that is one of the major issues. So how they fix the nitrogen? Obviously, I will talk about this how to fix this nitrogen at this level. So nitrogen fertilizers obviously needs some more focus. Because we have the phosphorus, we have the fluoride and potassium phosphorus, but nitrogen fixation is one of the major problems. So I will talk about that as well. So basically what I will be speaking about this is that we need a new technology that is basically now it's called a nanotechnology. And then I will talk about the nutrient use efficiency and the nanotechnology and nano fertilizers. Then formulation, characterization, and application of nanofertilizers. Then nanotechnology in increasing NUE, that is a nutrient use efficiency. Then what is the research saying? What has been done on this nanofertilizer? Then what are the problems with the nanofertilizers, nanotechnology? Then I will conclude with just giving the future prospects. Okay, the first one, the first and foremost one. I'm sorry, it's just hanging. Okay, so I'll just give some data and some technical terms what has been doing and what has been done in this crisis in this agriculture section. This is as you can see, this is the data of food grain production and fertilizers used in India. The red mark actually indicates that this is a fertilizer uses of fertilizer, and then the blue one indicates that this is a food grain production. Yeah, as you can see, from 1950 to 1980, the fertilizers use is less. So obviously, it is not even in the 50 points. So it is the fertilizers use was less. There was a reason why it was there was a less use. One reason is that the fertilizers research was not actually much focused. That means not much research was done. So there were not many type of fertilizers were available. Second is that most of the people actually depended on only the rain for the agriculture. So there was not like irrigation. You can use the water pumps to feed the plants. That was not there at that time. So especially in India, being a poor country at that time, we were not much fertilizers as used. Only fertilizers that were used was the cow dung, which is very famous still now. It is a very famous one, and the decomposition products of the plants that has been used for a lot of time. So there was no concept of fertilizers at that time in India. And the world, obviously, the world was also lack of fertilizers because of the unavailability of the fertilizers. So people were using other ways like organic matters for the for the fertilization. That is why the decrease was less. But look at the production. Production was actually absolutely fine. So now the question is that, so when the fertilizers use was less, why the production was more? Obviously, there were a lot of questions can answers can be done. The one first answer is that see, obviously the organic matter, the land was very big at the time. So like 10 acres, 20 acres, 30 acres, 40 acres. You can see in the movies you might have seen that usually landlord will have 500 acres of land. Now that is obviously that will be dream for anybody to own the 500 acres land. So the land was very much. The fertilizers that used was most of them was organic, and then the production was very high. Production not exactly amounting for the acres, for the land size of the land. It is just a production because there was a lot of land available. Obviously, when the lot of land available, you can grow lot of crops. That is the simple question. But now the population rise, industrialization has actually shrunken the land. And now the usage of fertilizers has been the most important topic in the agriculture section. Now, then you come to the from 1999 to 2011, you can see use of fertilizer has become more than the food grains production. So it is completely the very discouraging graph from the 2008 to particularly 2008 to 2011. Look at that. The production of the red mark has been already up in the case. This 249 to 273. That is a number which is using for the acre. That is for ml for an acre. And then the food production actually dropped in 2009 and 10. It has dropped quite drastically, and then obviously it is increasing, but it is not exactly encouraging increasement, because only use of fertilizer should actually enhance the food grain production of food grain instead of for decreasing it. So that is one of the things. So it has been discussed, and it has been debated. It has been tried to find the solution. There are the issues being faced as that, obviously, as I said, increasing the population that decreases the land. Then the stagnation. See, this is one of the most worrying problem that we're facing: stagnation in productivity. You cannot grow more than that. That is what the stagnation says. So particular land size will grow only particular amount of crop. That is very discouraging, because we need to grow more crops in a small size. That has been the problem. We are just 700 crores now. The world population is 700 crores, especially in India, 1.38. So 2020, we will reach around almost 200 crores people. That is that is a very huge amount. So where we will put the 200 crore people? Obviously, we will extend the urbanization. That we will extend our habitants. When we extend our habitants, obviously there will be decrease in the land. So stagnation is one of the things that we have to address. Then, as I said, limited arable land and water resource. Water crisis will obviously deepens when the population actually keeps on rising. Then the fourth one is that low fertilizers use efficiency. This is one of the things where we can do something. What we can do is that if we increase the efficiency of the fertilizer, or increase the efficiency of the intake of the fertilizer into the plant. Like if you use only 1 gram, all the at least 0.9 gram should be used by the plant. So what happens? The efficiency increases. Once that efficiency increases, obviously the crop size, crop production will be increased. So that is where we can address the issue. So that is when a lot of research has been done, is going with particularly with concerning to this one. This efficiency, nutrient use efficiency, basis. Okay. So now, so what is the need for a nano fertilizer? Why we cannot just use the conventional fertilizers? Conventional fertilizers has been very good for so many years. They've been really good in increasing the crop yield. There was very good in the plant, avoiding the diseases. They were very good. They were very good in making the plant very healthy, and also heavy efficient in food grain production. So, but what is the problems? There are some problems, the serious problems with the conventional fertilizers. One of the major problems that I have been not listed is that the usage of the conventional fertilizers is more. What is that means? You need more amount of conventional fertilizer to for the plant. So that means you have to use at least, I'm not talking about the scale, I'm just talking about hypothetically. One plant may need you have to use, for example, for one plant, you have to use 10 grams of fertilizer. That is a very huge amount. So what about the nutrient use efficiency? Plant will use only 1 gram. So 9 gram will be wasted. And wasted, that what is that means wasted? That will obviously go into the soil. So what it does with the soil, obviously it will kill the organic matters. And once the organic matter is killed, there will be decrease in the organic matter. Obviously, there will be the plant production will be. So this is one of the major problems with the conventional fertilizer. So the usage of amount is very much. Then there is a highly prone to losses. Most of the what happens is that which plant should be used for which fertilizers, whether this plant is to be used nitrogen fertilizers or not. For example, peanuts. The peanut plant is actually a it has a nitrogenase enzyme, which is actually which can have the capacity, which has the capacity to fix the nitrogen from the atmosphere and then make its own ammonia fertilizers, ammonia or ammonium nitrate or ammonium hydroxide. So it can make one. So now if you put again the nitrogen fertilizer to that, that is a complete waste, because peanuts have the luxury to make their own nitrogen-based fertilizers, but taking the nitrogen from the atmosphere. Then you are putting nitrogen extra. That means that nitrogen will completely not used. So that is one of the problems. That is why it actually gives the losses, highly prone to the losses. Second one is the major problem that has been listed is that pollution of the environment. So usage of the fertilizers, you know that fertilizers usage is actually a really problem. For example, when you take the spinach or what do you call it as the plants which you use to make the rasam sambar, those actually have the plants itself has the fertilizers. And what happens? That fertilizers will be taken from the taken to the body, and then probably the population or the people actually feel sick using those type of fertilizers. That is one of the problems. Second problem is that those fertilizers are insoluble in anything. So what happens? Those fertilizers will be again that they will be pumped into the rivers, and the rivers will be polluted. Even the soil pollution will be there. And worst problem is that these nitrogen fertilizers or the potassium fertilizers or the phosphorus fertilizers, they actually combine with oxygen to form the oxides. And we all know that oxides are the worst part of the metals. So what happens? Those fertilizers will be obviously lead to the problems with the soil erosion, soil pollution. So the pollution in the environment is the major crisis. You might have heard about the number of times fertilizers and the pesticides, two major pollutants in India, particularly in India. You heard about the pesticide debacle in Kerala, which actually killed so many people and which hampered so many people. So that is one of the problems. Then as I mentioned, low nutrient user efficiency. So you use 10 grams, but only 1 gram is utilized. That is a major problem with the conventional. So you can see the table which actually lists the efficiency and cause of low efficiency and the nutrients. A major nutrient, as I told you, nitrogen is the major nutrient for the fertilizers, which is 30 to 35%. So one of the most major problem with the conventional fertilizer is the immobilization. Immobilization, the molecule will be obviously big, or the nitrogen or the atom even is big. So now the problem is that the movement of these nitrogens. Why that is important? I will show in the next few slides how the nano fertilizers can be much more get into the plant easily compared to the conventional fertilizers. Since the conventional fertilizers are big in size, the intake of the plant will be very difficult. So they have to pass through the root and then to the stem and to the leaves. But that will be very difficult because if the molecule is too big. So one of the advantages of the nano fertilizers is, since nano is actually very small size, that is the one advantage. So it can actually go inside the plant very easily. I will show the picture of that. So that is one of the problems. Then there is a volatilization. A few of them are very volatile in that particular case. So there will be loss of efficiency. Then the denitrification, we will talk about that also. And then leaching. Leaching, obviously, removing of the nitrogen from the plant or from the soil. That is one of the major problems that we come across with the conventional fertilizers. Phosphorus, fixation in the soil, aluminum phosphorus, iron phosphorus, and calcium phosphorus. So what happens is that if the calcium is there in the soil, obviously it will bind to the calcium phosphate with the phosphorus and then forms the calcium phosphate. So what happens? obviously that calcium phosphate is completely insoluble. It is a very insoluble material. It won't be taken by the plants. So obviously there will be loss of fertilizer. So even though you put phosphorus fertilizers to the plant, since it has actually formed the calcium phosphate, which obviously becomes useless. So these are some things which actually come across conventional fertilizers. There is a potassium, there is a sulfur, so there is no fixation of these type of conventional fertilizers in the problems. So before I go into the further, I'd like to explain what is exactly the nutrient use efficiency. So what is nutrient use efficiency? It is actually you can give it as a mathematical term. It is like crop nutrient removal divided by nutrient input multiplied by 100. See, what is that means that crop nutrient removal is that you are actually obviously nutrient input is that how much fertilizers you are putting. Then the crop nutrient removal is that how much fertilizers is used by the plant. Divided by if you multiply that by 100, you will get the percentage of intake of the plant from the fertilizers. So how much used, how much was how much you put, how much was used by the plant, that will give the ratio of the nutrient use efficiency. That is just like when you eat food, iron food, for example, how much iron is absorbed is very important than how much you eat. For example, if you eat 1 gram of iron every day, but your body only absorbs 200 milligram, so the another 800 milligram will be wastage. It will just go out of the system. So that is one of the problems. That is why we need to increase the nutrient use efficiency. So this is very well given. You can see the picture, which actually this is a metal organic nutrient that has been used. You can see the plant is actually taking, and then once the plant takes a better amount of fertilizers, obviously it will grow better food production. That is the issue. So why it is important? Obviously yield is important. For example, if you are using 10 gram, if the 9 gram is taken by the plant, that means your crop will be your efficiency will be high, your use of your fertilizers will be high, and also moreover the crop production will be more. So yield is first one. Second one is economics. So that means you don't have to put fertilizers again and again and again and again. For example, if you are putting 10 grams, it actually absorbs 9 grams. That means it is more sufficient for the plant to survive with that fertilizer. If not, be taken inside, and again you put 10 gram, another 1 gram. So what you are doing is that you are actually wasting the fertilizers. That is why economics comes to the picture. The ecology, as I told, these metal fertilizers are really dangerous for that particular, because they combine with organic matter and then form the problems. So that is ecologically, obviously, you know that will cause the pollution to the soil, and also that soil, when the rain comes, it will go to the sea, and then it will also kill the aquatic animals. So it is ecologically disturbing using the conventional. So that is why nutrient use efficiency is very important, and obviously health is associated with the these productions. So what is the solution for this? So how to approach this increase in NUE, that is a nutrient use efficiency? So there are cultural methods which have been using for a long time, centuries, using the conventional nitrogens. So nutrient placements are foliar spray. You can see the people actually use the fertilizers using the spray. That's a foliar spray that is used. Then there is a management aspect. Management aspect actually combines with the chlorophyll. There is a management aspect in the plant itself. So there is a chlorophyll content, there is a LCC, SAPD meters, and a SSNM. These are just technical terms for the management aspect. Then what we do is that the best approach will be novel fertilizer production method. So that is the nano fertilizers. So we can actually replace the conventional fertilizers from the nano fertilizers for the efficiency, for the less pollution, for the ecological aspect, and for the health aspect as well. So that can be done with the use efficiency. I'm not going to these terms. So these are very technical terms. They are available in any books. This is actually taken from the Mysar et al. In 2004, which he published. So there are like what is the efficiency, what is the physiological efficiency, and the apparent recovery efficiency. If you're really interested, you can actually, it's available. It is self-explanatory. You don't need anybody to actually explain this. This is a very mathematical terms. So I will come to the final sorry. Now audible, sir? Hello. Okay. Hello, sir. Okay. Okay. Thank you. So the nanotechnology was obviously coined by Norio Taniguchi from the Tokyo Institute of Technology, who was very famous, first person to coin this nanotechnology term. That comprises of nanoparticles and also other things. So he actually said that obviously Richard Feynman was the one first said that nanoparticles will be very important. He said the famous word that is saying there is a lot of room in the bottom. That is the famous phrase he used. That actually means that there is a lot of room in the bottom. That actually means that it is if you go smaller smaller size, you will get more productivity. That is what he actually meant. And then based on that, this guy, Professor Nario Taniguchi, he actually coined this nanotechnology based on the Greek word. Nano means dwarf. So anything which is smaller is called nano. So that is nano. You all know that it's a 10 raised to minus 9. In the mathematical term. So it's around 1 to 100 nanometer. Anything which is below 100 nanometer is called a nanomaterial. So above 100 nanometer will be micron. So that is how they actually kind. You can see the left side, there are the incidental nanoparticles. So nanoparticles are the particles which have the smaller size, below 100 nanometer. And then there is engineered nanoparticles, which are more defined. One of the major problems with the nanotechnology or nanoparticles is the what is that? The reproduction. You cannot actually synthesize same sized nanoparticles with the second time. So the reproduction is one of the major problems. But in the engineered nanoparticles, that problem is addressed using different methods. So the engineered nanoparticles are much more application oriented, much more stabilized compared to the basic nanoparticles. So these are the nanoparticles that the term you can actually come across. I'm not going to this. This is very basic for anybody. But I thought of people who are actually beyond the chemistry or beyond the nanotechnology, they can actually understand. So this is a nanometer. You can see. Human is, for example, 1 meter, and while atoms is 0.1 nanometer. For particularly atoms, actually, that hydrogen atom is around 0.1 nanometer. So nanometer size means that you are actually making the material, the bulk material, to the nano size, to the hydrogen size. Hydrogen is 0.1 nanometer. So DNA is around 10 nanometer. So DNA is also a nanoparticle. And then you can see the virus. The coronavirus is actually believed to be around 80 nanometer. That COVID-19, which is actually keeping us at home, which is around just 80 nanometer. Look at the 80 nanometer virus is actually destroying whole system. We have been completely become, we are in the crisis mode particularly. So the nanometer size compared to this nanometer, so bacteria is 1 micrometer. So bacteria is bigger compared to the virus, and then anything below virus is actually called the nanometer. That is a size comparison. That is the size of the nanoparticles. What is the unique properties of nanoparticles? There are two important. I have listed some of them. You can see the slide. That is not an issue. But two major things which really attract the nanoparticles is the size and the surface area. So when you take the bulk material, the surface area will be less. But when you just keep on cutting that bulk material into the nanoparticle, you are actually increasing the surface area. So surface area is one of the major problems, or major advantage with the nanoparticles. Why? Because most of the reactions that occurs in the human or in the nature, even in the industrial production, there are actually most of them are the surface reactions. So more the surface, more the reactions, more the reactions, more the productions. That is how it actually works with. That is why the nanoparticles are very appealing. Everybody is working with the nanoparticles. Even people who have never actually come across the nanoparticles are working. You can take my example. I am a pure organometallic chemistry guy, but now I started working with the nanoparticles. We have actually got a very good results with the nanoparticles. I'm combining the surface with the organometallic chemistry. That could be really appealing. Anybody, it is the topic which you cannot resist. So that is one of the advantages, larger surface area. And then another thing is that smaller size. So nanoparticles can be fixed anywhere. anywhere. It's just like fixing the atoms. So you can fix that anywhere. So you can avoid the bulk materials. That is one of the beautiful of the nanoparticles. Of course, there are problems with the nanoparticles that I will discuss at the end. But these are the two major things that actually comes across. Small size and the large surface areas are very appealing for any chemist or any physicist or any biologist to work with these type of materials. Small is much more smarter. And another two, which you can see in the last, they are actually slow release, particularly concerned with the nanofertilizers. I will talk about the slow release and the fast release, and then the specific release as well. So what happens is that nanoparticles actually have the slow release comparatively. Engineered nanoparticles have the slow movement, slow immobilization, so they can be slowly released into the atmosphere. Well, the conventional fertilizers cannot be done because they are actually very fast in the release. So it is just like fast things usually end up with the problems, while the slow things usually end up with the advantages. That is the two major issues. And other things you might have known this, and most of you might now know how to synthesize these nanoparticles. Now everybody is actually synthesizing the nanoparticles one way or the other way. That is very encouraging as well, because it increases the efficiency of a research. And then you know that one of the major problems with the nanoparticles is the characterization. For an organometallic chemistry, I used a single crystal XRD, and NMR was the measure for us. NMR and a single crystal XRD would be enough. But and they were cheap. Comparatively, equipments are cheap. But if you come to the characterization of nanoparticles, you need to use different techniques, particularly SEM, TEM, tunneling electron microscopy, scanning electron microscopy, then powder XRD. Obviously, then you have to use the EDX. Elemental analysis for the elemental analysis. So those are the somewhat expensive, but worth for the nanoparticles. Then the third one is the application. You can see the increase in the applications of nanoparticles. People are actually using nanoparticles for everywhere, whether it is a biomedical, whether it is a material, whether it is an engineering, whether it is a the conventional chemistry or physics. People are using the application, finding the applications of nanoparticles in everywhere, particularly everywhere. You might have heard about if you go through the recent publications with the nanoparticles, particularly with the COVID, they are using for the COVID as well. So there are two approaches. You might have known these things: a top-down approach and bottom-up approach. So top-down, that you take the bulk material and then you keep on cutting that material into the pieces, and then you finally end up with the nanoparticles. Bottom-up approach is that you take the the smaller atoms, and then you try to make it the nanoparticles. These are the two important. So you can see at the right side, this is a top-down approach. So you take the bulk to make the nanoparticles, and then in the bottom up, you take the atoms instead of bulks. You take the atoms and then make it a cluster, and then the nanoparticles. So there are two efficient methods. Both methods work very fine. That is not an issue with the methods. And one of the advantages with the nanoparticles that you don't need much to synthesize nanoparticles. Of course, characterization needs somewhat luxury, but synthesis is very easy. You need only these materials. See, I started with these nanoparticles only with this: a beaker, conical flask, magnetic stirrer, magnetic bead, and burette. You need only these type of materials, so that these are available in everything. So you don't need to work for the funding, where to get the funding, what to get the funding. There's no need. There are common materials available for iron oxide, for example. Iron nitrate is available. You take these iron nitrates and then actually work with the nanoparticles. So very minimum for synthesis of nanoparticles, very minimum equipments are required, very minimum instruments are required. Only characterization is, if you know anybody in the characterization, you can actually do this very good chemistry with this. So this is a checklist for the, and as I said, this is one of the problems with that. We need these type of equipments. Tunneling transmission electron microscopy, that is also called tunneling electron microscopy. Then SM, scanning electron microscopy, and then dynamic light scattering, and then powder XRD you need. Some more instruments are needed. The only problem with these instruments are they're a bit expensive. So these are available. You can actually look into that. With the time limit, I can't explain. So these are some images of the SEM and TEM images of the nanoparticles. Look at the titanium oxide, selenium oxide, zinc oxide, and silicon oxide. You can look at the SEM image. So beautiful SEM image. How the nanoparticles are formed. Look at this iron oxide, which is fantastically beautiful, round this spherical shape. And then you can see the zinc oxide, which are also spherical shape with the tubes on that. So that is kind of these can be obtained with the TM and the SEM images. So these are available. So what is the properties? Why we are more interested is that as I told you, high surface area to volume ratio. First one. Second is that second is high mobility, because they are small in size. The mobility will increase. Then they are more efficient compared to the conventional. Okay, so this is one of the action that what is what is nanoparticle doing in the exact what is happening. The nanoparticle, this is particularly copper oxide nanoparticle. That is, this is what you are seeing is that root. That is the root entering of the root, and these are what you are seeing is that nanoparticles, copper oxide nanoparticles. Look at that, they are entering. This is taken with a high resolution TM image. See, that means what you are seeing in the left side, which is a hypothetical one, you can clearly see with the right side, which is with the instrumentation, which is not obviously which cannot be done with the conventional fertilizers. So if you use conventional fertilizers, they are too big, so their intake will be very small, and even you cannot actually measure with the other images. So this is one of the things that mode of action is taking place. So nano fertilizers used for the roots, and then the roots actually take these nanoparticles inside the stem, and then they will actually put into the next productivity. So there are very different approaches has been done, as I told you. Some people actually use the nanoparticles as it is. Like, for example, iron oxide nanoparticle, they use just to the plants, and then they grow the crops. That is one thing. Second thing is that engineered nanoparticles. Engineers are very smart in that case, because they usually make it a more methodological compared to the basic science people. So what they do is that they encapsulate. Encapsulate is when they put these nanoparticles, few nanoparticles in one capsule, just like putting a powder of the medicine powder into the capsule. So what you do is that encapsulation, and then they put into the nanoparticle. So instead of one nanoparticle going inside the plant, it can take some 10 nanoparticles with the encapsulated, and then taking into the particle. So that would be much more efficient. That is a very smart use of fertilizers. Then what happens with the encapsulation of fertilizers is that a slow delivery. So what happens that the encapsulated particle group will go into the plant, and then they start opening the encapsulation. They decapsulate. So then the particles will enter into the problem. So instead of nanoparticles directly going to the plants, so that can be done with that. That is a very smart one. That will actually enhances the slow delivery. Then there are smart delivery system. So the smart delivery system also includes sensors and other things which can be protected from the which crops can be protected from the even the birds, or you might have heard about the recent the crickets, the what is that locusts, midte. So the locusts were was the delivery system. That is another thing. So with the biosensors, especially, you can avoid that locust type of system, which has been tried in recent times. So these are the approaches of the NUE, particularly with the different. So as I told you, encapsulation is that making one group of nanoparticles and putting in the one encapsulation. You can see this is a shell. The round one is a shell, and then the inside are the nanoparticles. So instead of one nanoparticle each time, you can take like 10 or 15 or 50 or 100 nanoparticles in one time, and then take into the plant. That is a very smart way. So this is kind of a packaging the nanoparticle fertilizer and then using it as a shell. So what happens is that advantage. What is the advantage is that for example, if iron oxide actually goes into the plant, what it will convert into the iron hydroxide. That is a problem with the iron oxide taking into the plant. If you take single iron nanoparticle, when it enter to the plant usually have the water in that. That water will combine with the iron oxide and then forms the iron hydroxide. Well, that iron hydroxide is not soluble at all, so it will be useless most of the time. It doesn't happen all the time, but few nanoparticles will encounter that. So if you encapsulate, that will be avoided. So there will be no treatment, no interaction with the water. So the nanoparticles go enter into the leaves without any problem. So that is one protection. Then obviously there will be decrease in solubility because of the bulkiness. So there is a decrease in solubility, means that they will not be wasted. That is another advantage. Then as I told you, uh, sometimes what happens that these nanoparticles, encapsulated nanoparticles, are very safe to use for the agriculture people. So they don't have any problem with the nanoparticles, because at the end you will see nanoparticles are toxic materials. So what you do is that you can encapsulate. Once you encapsulate, the farmer which is using these nanoparticles will be he will be safe. That is another advantage. Obviously, and another one is that environment reducing runoff rates. That is been debated, whether it is a good for environment or bad for environment. But it is positive consensus that that is a good for environment. Encapsulating is the good for the environment. That has been noted. This is a slow delivery. I will skip for that. I know we have, sir. Where is sir? Sir, how much time I have? Oh, then it's then I will go through. Okay, that's great. Okay, so yes, so this is one of the things that I would really love to speak about, the smart delivery system. So what is smart delivery system? This is actually applies to the biomedical as well. For example, people who are suffering from the cancer, they've been treated with a targeted molecule. What is targeted molecule? Is that that molecule only goes to the cancer cell and then kills the cancer cell instead of doing anything to the healthy cell. Same system is, this is a smart delivery system. Smart delivery system actually identifies the target and then you only interacts with the target. If you think of any, for example, if you look at the people who are actually suffering from the cancer, if you radiation therapy or chemotherapy usually gives a lot of side effects. Why that side effects happens is that because this targeted delivery, instead of this that medicine, instead of going to the, not only the, it does not, it not only kills the cancer cells, it also kills the healthy cells. When the healthy cell is killed, obviously the person will feel the side effect. It may be due to the death of the healthy cells. So if you use smart delivery system, what happens if with the smart delivery system? Smart delivery, that is a very beautiful thing that can be done. Same, you can see the nanoparticle in the picture. You can see the nanoparticle, and this is a targeted molecule. Just like your anacin actually cures your headache, but it doesn't actually cures your stomach pain or body ache. It doesn't. It only cures the headache. See that, what is that? Is that is a targeted delivery. Aspirin doesn't take the cure the stomach pain, and why? Because the aspirin is actually designed to make the only with the headache, deal with the headache. This is what the targeted delivery about. So smart delivery molecules usually target the molecules and then they fix the target and then they end the problems. Here what they do is the targeted molecule, that is in the body system. But in the plant system, what you do is that you take the nanoparticle and then targeted molecule and then use the drug and then use the targeted element. Here also, what you do is that if the plant is diseased, for example, if the plant leaves are diseased, now the stem is fine, only leaves are diseased. Now, if you use just nanoparticles like that, they will disrupt whole the system. So what they do is that if you use a smart delivery system, that nanoparticle will go only to the leaves and then cures the disease, and that will go to the only diseased leaves, not all the leaves, only diseased leaves, and cure the disease. That is the beauty of the smart delivery system. So this is one very difficult to achieve, but a lot of effort has been taking place. A lot of people working on this smart delivery system. So you can see this is available in the time. You can size, you can actually modify the size depending upon the target. You can modify the surface area depending upon the target. You can actually self-regulate the system on their pre-program, and then even also avoid the biological systems. As I told, what this contains a lot of water molecule. Plant contains water molecule. That water molecule will interact with the nanoparticle that completely avoided, and then some smart delivery system will go to the where the problem is, then that will fix the problem. So that is one of the beauty of the smart delivery system. And as I told you, nano biosensors are being used. Sensors are very important to see whether this what you are feeding is going to the where it has to go. That is the biosensor do. It is just like monitoring. You can see the MRI, for example. MRIs are the scanning materials. What they do is that actually they give the medicine, and then they will observe the medicine where that is going, and then where it is actually taking. Best example that the people with the heart disease or the heart block, they actually have this stent. So stent, if you have a chance to go to the medical, the college or the people who are actually putting the stent, you can actually see that where the stent is going through the scanning. Like that, biosensors will monitor about the nanoparticles going into the body. That is the beauty of the nano biosensors. So a lot of work is going on with the nano biosensors. And also, as I told you, nano biosensors can be used to detect the birds and then make them fly away from from not feeding the crops. So that is what. So protecting the crop from the birds is also one of the important with the nano biosensors. These are the method of application. So you can use nanoparticles for the various purposes. As I told you, everybody is behind the nanoparticles, but it's very good thing, because when more people involved in the nanochemistry or nano fertilizers or even nanoparticles, that is a welcome step, because someone will come up with some great idea, and then we can actually solve some problems. That would be the beautiful thing. There are nanoporous zeolites that has been used. I have a couple of slides for that. This is mainly used for the leaching, nitrate leaching. So removal of nitrate for the even leaching. You might know the zeolites. They are part of metal organic frameworks. So they are big molecules with a lot of gaps in that. So those gaps will be filled with the leaching agent, and then that will be carried. It is their zeolites are used for the hydrogen storage as well. So you can store the hydrogen in the zeolite. And there is interaction is not actually chemical interaction. It is a very physical interaction. So that hydrogen will go and just sit without doing anything, just sit there, and then the zeolite will be taken to anywhere it went, and then when you want hydrogen back, it will give the hydrogen without any interaction. So these zeolites are used in particular case. So now I'll finally come to this research findings. What has been done? So now I talked about how important the nanofertilizers. They can be really promising. That is all theory. But if you ask me, what you show me the proof that they are better, I'll definitely give the proof of some of the nanoparticles which are being used extensively, and then that increases the crop productivity, decreases the diseases in the plants, increases the crop yield, and also increases the efficiency of the nutrient. So those are the research findings that I am going to talk about. These are the iron oxide nanoparticles that we prepared in our laboratory. This is we did in both the methods, so bottom up approach and the top down approach as well. So in both cases, it works very fine. This has been very established things. So this, you can see there's a 10 nanometer. You can see the scanning electron microscopy, that is which shows that this is actually the engineered nanoparticles. So we actually encapsulated with
ಅಲ್ಲಿಂದ ಆರಾಮಾಗಿ ಅಷ್ಟೇ ರೀ. ನಾನು ಈ ಪ್ರೈವೇಟ್ ಯಾಕೆ ಹೋಗಿ ಸೇರ್ಕೊಂತಾನ ಚಾರ್ಜ್ ಮಾಡ್ತಾರಂತ ಗೊತ್ತಿತ್ತು. ಹಂಗಿದ್ಮೇಲೆ ಪ್ರೈವೇಟ್ ಹೋಗಿ ಯಾಕೆ ಕೊಂಡ್ಬಿಡ್ತಾನ? ಚಲೋ ಬೆಡ್ ಹಾಕಿ ಮಲಗಿಸ್ತಾರೆ ಅಷ್ಟೇ ರೀ. ಅಷ್ಟೇ ಗೌರ್ಮೆಂಟ್ ದವಾಖಾನೆಗಳು ಅದ ಮತ್ತೇನ್
somebody is talking about it. Yes. Okay, thank you, sir. So these iron oxide nanoparticles are very easy to prepare. So what we are doing is that why iron? Again, as I told you, I'm more interested in nitrogen fertilizers, and it is believed that nitrogenase enzyme is actually a iron compound with a iron sulfur compound, which actually able to fix the atmospheric nitrogen and then make the ammonia. So that is why I'm more interested in iron. That is what I learned in University of Rochester, New York. where I did bioinorganic chemistry, where I used simple iron compounds to make the fix the nitrogen. So I'm using here iron nanoparticles. So that is why it is related. See, I am much more related to the this nanofertilizers. So this is the nanofertilizer. So you can see this has been these nanoparticles are used in the plant. This is one of the papers which is published in 2017. It's here in the down from the Chowal and people. You can see these are the what you see in the left side, the parts. You can see the parts which are actually feeded with the different parts. Ones are the uses of the nanoparticles, and these nanoparticles are used in a different amount. For example, 1,000 nanoparticles or 100 nanoparticles or the 2,000 nanoparticles. So the size, the amount of nanoparticles used was different, but there were the very encouraging results. On the right side, what you are seeing is that urea. This urea is actually this is a conventional fertilizers, as you can see. Urea is a very conventional fertilizer which has been used for a long time. And what you are seeing in this slide, particularly the big slides, is that left side, the plant which is actually feeded with a nano fertilizer, and the right side, the plant which is feeded with the urea. That is a conventional fertilizers. Look at the difference between them. The left side is actually much more greener than the right side, because the right side is actually disease with the diseases and as well as a early productivity. That means they give the production. For example, if it has to go 3 months, it is growing early production. That means 2 months it is already giving the crop. So what happens? The crop yield will be decreases. So, but look at this left side, which is used in the nanoparticles, which are it is actually done in the bulk cases. The Agriculture University has done this experiment. So they put it in not only acres, few acres, hectares. They put it in hectares, the nanoparticles. Usage of nanoparticles was less, but the productivity is very high. And what has been observed that the plants were very, very healthy. There was no disease found whatsoever. But if you look at the urea, that is the conventional fertilizers, there are still problems. There was no loss of nutrients again. There was a disease. There was a early production, and there was a yield of the crop is very less. So this you can see clearly that nano fertilizers are much more better than the conventional fertilizers. That's one. This is iron oxide based. So just preparing iron oxide nanoparticle and then use them. There was no encapsulation, but we are doing encapsulation in our laboratory. The second one is that a lot of work has been also done on the other base, particularly, for example, zinc oxide, then nitrogen base, phosphorus, and then the potassium, and other stuffs, which are also very encouraging based compared to the other. So, for example, this is the silver nanoparticle. So most of the times I go with the data, because data will tell much better than the just telling bluntly on the air. So this is the effect of silver nanoparticles on the yield of attributes of wheat. So they used silver nanoparticles in the wheat production. So you can see left side is the treatment, then number of grains or spikes that indicates a crop production. What is the weight of under grains, and what is the yield versus part. So if you look at this, there was no first line is that this one indicates that there was no use of nanoparticle. So 0 ppm, that means no use of nanoparticle. Look at the grains, number of grains, which is 18.5, and 100 grain per weight is 3.35. That means it is not exactly very healthy. I mean, it is not very. It doesn't have very much flour in that grain. Then the yield is yield per part is 7.18. That is 7. So each part gave 7.18 grams of wheat, and each grain weight is actually very less for 18. But when they use of iron silver, look at the difference in the weight. First line is the no use silver nanoparticles. Second line indicates the usage of silver nanoparticles, which is around 20. Without nanofertilizer and with nanofertilizer, particularly without silver nanoparticle and with silver nanoparticles, there is a quite increase in the number of grains per spike, and there is also increase in the weight of each grain. So 100 grain gives 4.66, which is against to 3.35 without the silver nanoparticles. Then look at the yield. Yield is almost doubled. It is doubled. The yield has become completely doubled compared to the one part. So one part actually gave around 13.25 grams of wheats. So that is amazing, silver nanoparticles. But now, it is always the question that comes into the mind. Okay, now I use 25 ppm. What if I use 100 ppm or 50 ppm or more ppm? Okay, that is this is fine. 25 ppm is fine. 50 ppm is like a greed. Okay, if I put 50 ppm, I can grow it much more better. That won't work like that. Usually, science won't work like that. Women can be greedy, but science won't be greedy in that. So they use 50 ppm. But look at the decrease in the problem. So there is a decrease in the number of grains, decrease in the 100 grain weight as well, and the decrease in the yield as well. So what is that? Is that is called cytotoxicity. Cytotoxicity, that you can eat how much you can eat. You cannot eat something like three times food at one time, because you are not adapted to, you are not made to used to. You will get into the problems. Similarly, you cannot feed more than what plant can receive. So it can really harm, because it will do unwanted things. Extra. That is what exactly happens with the conventional fertilizers. You use a lot of fertilizers, productivity will become less, because there is other extra fertilizer that is unused will do nonsense. Exactly same thing. So 50 ppm, 100 ppm, 150 ppm, no, nothing actually gave the much better than the 20 ppm. So what happens is that if you use more amount of nanoparticles, it will obviously problem starts with the cytotoxicity, where the instead of increasing the production weight, it actually becomes adverse effect, and then starts decreasing the production weight, and also gives problems to the plant itself. It gets into the diseases. So this is what problem with it. So optimum usage of silver nanoparticles for the wheat is 25 ppm, which actually give the better results. So you can see these are the as I showed in the previous slide, the parts which were used for the silver nanoparticles, that depicts the how the plants actually grow with each particles. So it is not necessary that if you have produced silver nanoparticles or zinc oxide nanoparticles or iron nanoparticles, you have 100 grams of iron nanoparticles. It is not necessary that you use 100 gram all that together. You have to optimize it. So optimize needs a few experiments, different sized and amount of nanoparticles will be tested, and then once nanoparticles is stabilized, optimized, that can be used for the productivity of these materials. So this is what happens in the case of silver nanoparticles. Again, this is content of the phosphorus and the sulfur. So you can see 25 ppm actually works very well for the nitrogen efficiency, phosphorus efficiency, and potassium efficiency. So others will be keep on decreasing, and no nanoparticle will also be lesser. So if you use no nano fertilizer, you get 69.75 usage of nitrogen, while with the 25 ppm, you get 74.25. So similarly, phosphorus use efficiency increased, and also potassium use efficiency increased. That means nanoparticle is definitely helping the plant to use its nutrients well, and also use the better crop productivity, and also it is disease free. That is what I want to say in that. So these are the experiments. So not only stem, not only leaves, it also increases the roots. This is one example of the zinc oxide, usage of zinc oxide in the plant. So zinc oxide is it. The center one is 1000 ppm nano size zinc is used. This center one. Look at the root. Root has become so drastically much more stronger, much more deeper into the soil, which gives them much better productivity. So it is not only stem or leaves which are bothered, utilize the nanoparticles. It is the root that is actually also use these nanoparticles very efficiently, and then grow in a better way. So you can see the difference between the nanoparticles, conventional particles, and the bulk particles. This is a control. Look at this. There is no root at all. So this is actually gives, and this what happens that it is increases the efficiency of the crop. That is one of the advantages. So higher root growth in case of zinc oxide treatment with 1000 ppm, and higher plant growth in case of zinc oxide with 1000 ppm. So the plant is also increased. You can see here the right side. This is a 1000 ppm nano, this is 1000 ppm bulk, and this is a control. So look at this 1000 ppm nano, which is a healthy, very height also increases. The plant looks very healthy, and also moreover the production and root is also becomes very efficient. This is using the zinc oxide treatment. So there are a lot of research has been done used with a bulk zinc sulfate. Zinc sulfate is the common nano fertilizer that is available in the market. If you ask for the zinc nanoparticles, you will usually use zinc sulfate. That is a bulk one. So you can look at this 1000 ppm. That is obviously what you are seeing in the red is the nanoparticle. The others are conventional or bulk or the control. So look at the 1000 ppm. It is actually showing much more better root dry weight, or the number of parts, or the plants, or the part dry. Everything is actually much more compared to the other nanoparticles. So what is actually says, this data says that a nanoparticle, the zinc oxide, nanoscale zinc oxides are much better compared to the bulk zinc sulfates. So again, the efficiency of the phosphorus and efficiency of the potassium also, and efficiency of the nitrogen, they are very efficient. The absorption of nitrogen, absorption of the phosphorus, absorption of the potassium is very helpful in case of nanoscale zinc oxide, which is not available in case of a conventional. So you look at the 43.8, 16.8, 83.90. Look at these two datas. It is very encouraging. So what it is actually indicates that if you use zinc oxide, nano scale zinc oxide for the crops, that gives the better efficiency, better production compared to the conventional and the bulk one. So like that, there is a lot of work has been done on everything, not only on the productivity, not only on the root. It is also done on the diseases. It is also done on the the efficiency also. So you can see this is an experiment. This is the effect of nano zinc oxide and the uptake of the zinc. That means it's a nutrient use efficiency, NUE. So NUE is also much better. Look at this; these are all in 40s, while the with the conventional they are only in 30s. So this actually shows that there is a intake. So zinc oxide can go into the plant much better than the conventional zinc sulfate. That is what I'm saying with the effect of zinc oxide. So effect of zinc nano fertilizers on pearl millet. So it's not only one plant they have tested. They've tested on the millet. They've tested on the wheat. They've tested on the peanuts. They've also tested on the carrots. So they actually listed, and it's very encouraging that all the plants, irrespective of which plant they used, there was a only advantages has been seen with the zinc oxide nanoparticles compared to the unadvantages. All the plants actually showed very remarkable efficiency, remarkable activity, remarkable healthy stems and leaves compared to the other conventional summers. So this is one of the things that is very encouraging in many cases. And another term which comes with is that another comes with as a solubilizing enzyme, the enzyme activity in rhizosphere of 6-week-old pearl millet. This is a pearl millet. So P solubilizing, the phosphorus solubilizing enzyme. So what it does that usually phosphorus forms a calcium phosphate or metal phosphates, which are very difficult to soluble. So what this zinc oxide is that it actually control the phosphorus solubilizing. So it actually helps the solubilization of the phosphorus, and then that will be obviously taken inside the plants. That is what it has been done with the P solubilizing enzyme activity. So that also shows the very positive results. And then the effect of different concentration. These are the copper nanoparticles on the growth parameter of wheat. Okay, after 4 weeks. So they used copper nanoparticles also for instead of zinc particles, and then they found it they are also very helpful to grow the better crop and better plant system compared to the bulky copper sulfate nanofertilizers. So the data shows very promising results if you use the copper nanoparticles as well. So you can see here, these are the NHA, that is a nano-sized hydroxyapatite, that's called NHA. So you can see the different plants from left to right. This plant actually says that this is used NHA, and these are the simple conventional fertilizers that has been used. So they are actually weaker compared to the nano-sized hydroxyapatite. So that also shows that this is a soybean plant. So this also shows that NHA, that is a nano-sized hydroxy apatite, is much more better compared to the conventional nanoparticles. That is another thing that comes with the soybeans. So that again, the nano phosphorus also used for the testing, and they showed that soybean is actually giving much more crop yield and much better productivity compared to the unconventional. So these are the lot of work has been done. Look at this. This is one of the data that shows what if we use different variants, different treatments. For example, the blue one at the right side, they did not use any fertilizer. No fertilizer with phosphorus or nothing, just a tap water. So look at the productivity. It even though it is increases, but it is way below than the others. So the tap water only gives some productivity, which is obviously without the fertilizer phosphorus. But if you use fertilizer without phosphorus also, that actually shows similar as a tap water. That means there is no difference between using the fertilizer without phosphorus. So they and tap water, they are both same. But if you use fertilizer with regular phosphorus, it gives very increase in productivity. Just a regular phosphorus, it's a conventional fertilizer. So that actually shows the very increasing. But finally, if you use fertilizer with NHA, that is nano-sized hydroxypeptide, look at the production. Very, very, very high production. It actually there is a difference between almost 40 numbers, 40 plant height. That the height of the plant is actually becomes 40 centimeters. So that means NHA actually gives the better plant extract compared to the other biomass. So as I showed, this is what. So the left side, what you are seeing, that this is a nano NHA used. So look at this as how much height is, how much healthy it looks, how much full it looks compared to the this tap. This is a tap water. This is a fertilizer without phosphorus. This is a fertilizer with phosphorus, conventional fertilizer, and this is a NHA, nano fertilizer. So look at that. That's a very encouraging and very healthy productivity. So these are the lot of data is available. If you're interested, you can actually go through the this Heba et al. Egypt. That's 2016. There are a number of papers available. People actually worked very hard to optimize these nanoparticles production. So there are many data available based on that. Another important is that controlled release. Controlled. This is one of the important aspect. So what happens is that in the bulk there is no control of a release of a fertilizer. But in case of nanoparticles, there is a control. That means you give one nanoparticle at one time. That is what I'm saying, is that it's hypothetical. Again, I'm saying that there is a control release of particle in the case of nanoparticles, while there is no control release of fertilizer in case of conventional fertilizer. So you can see here, this data indicates this is a zinc release with a ppm level. This what you see in red is zinc sulfate. That is a conventional nano fertilizer, conventional fertilizer. And this one, the green one, is a nano fertilizer. Look at the slow delivery. So it is going very slowly, and then coming to the optimum. While in this case, zinc sulfate, it actually going quite fast and then release very fast and then come to the stabilization. So it is what happens is that zinc sulfate will not only harm the process, it will also form something unwarranted compounds which are not useful. But in case of slow release, complete it increases the NUE, nutrient use efficiency. That slow release will increase. That is why nano size are much better compared to the conventional polymers. So that is what has been said. Again, this is nitrate leaching. That is a removal of nitrate. It has been found that zinc nanoparticles are very zeolites are very useful in case of nitrate leaching. This is the data indicates that the left side, the white one, that without shaded, there this is what is it, NO3 and release with the different sizes. This is a 20 gram per kilogram that nanoparticles used. This is a 60 gram per kilogram. So if you use 20 gram per kilogram, you see the definite nitrate leaching compared to the 60 grams per kilogram. That means optimum is better. So usage of less nanoparticle will give the better nitrate leaching. So these are the productivities. So there are a number of studies has been done with the roots, taking the roots absorption, taking the stem, taking the product that's seeds as well. A lot of experiment has been done. So As I told you that these are the I just used the many data so that to make sure that what people are doing, they are actually consistently getting the uh, very good results, consistently very good results. There are very less papers which actually says that the nanoparticles were harmful. There was no, actually literally to the best of my knowledge, I did not see any paper which actually says that nanoparticles are not good for as a fertilizers. Most of the particles actually come with the idea that the nanoparticles are better than. So before concluding that, I would like to see this is a comparative statement, comparative the data. I mean comparative of every data with the sized fertilizers. There is a nano fertilizers with the conventional fertilizers. So if it is use conventional agriculture, look at the plant also. You can look at the plants also. So that actually says that efficiency and productivity and the height. So there is a low productivity, stress and disease sensitive, then nutritional deficiency with the conventional fertilizers. As I told, these are the three major things which affect the crop yield. Then the poor soil biological health, low native nutrient mobilization, and then low microbial diversity. When you come to the organic agriculture, now you can see everybody is saying organic. Organic. So what is exactly organic is that they usually don't use nitrogen, phosphorus, potassium-based fertilizers. They use this cow dung and other decomposition materials as an organic matters. So now, especially in developed countries, in USA, it is to buy organic vegetables. Uh, they are very expensive indeed. They are very expensive because the availability of organic matter, organic fertilizers is very less. That is the problem. They are very expensive. But if you look at these things, they are not much difference. I used both the vegetables, but I never found there is a difference between the organic vegetables and the simple inorganic or fertilizer, conventional fertilizer used products. I did not find the taste difference. I did not find any much difference between the organic matter and the conventional agriculture. So it is just a hype that this is organic, this is organic, this is organic. But nitrogen is needed for the body as well. So if the organic also same low production rate, only one thing is that it says that it is nutritive food, but I'm still skeptic about the nutrition of food, but I did not find any difference. Even most people did not find the difference. Even the study did not find the much difference. But yes, there is some increase in the nutrient food because organic matter is much more absorbed easily compared to the nitrogens or phosphorus or the silicon. Then one of the advantages of the organic agriculture is that it improves the biological health because it is an organic, obviously. That is why it increases the biological health. Then if you use bulk one, obviously high production rate, bioaccumulation and harmful fertilizer product, that is the problem. Side product will be more, that will be pollutants. Then the effect of natural resources, because if you're using bulk, obviously it will affect the bulk natural sources. That means you are keep on using the nitrogen or keep on using the phosphorus, keep on using the potassium. What happens? You obviously run out of the phosphorus or the potassium. Mining will be done. So that will be the one problem. So natural resources will be affected. Then the decrease in nutritional quality that has been observed in the bulk fertilizers. Demolish soil biological health. Irrespective of whether it is a nano fertilizer or conventional fertilizer or organic fertilizers, one problem is there that they're all pollutants because they are extra. Like you are taking a medicine, whether it is a chemical medicine, particularly chemical medicine, that is very harmful. So if you are taking anacin, you are actually affecting your body because that cannot be avoided. So like that, every has the disadvantage. But that is a very common thing that is available in case of every fertilizers. But look at the final one. This is a nano fertilizer mediated agriculture. The production is very high, more nutritious food, save natural resource, and then sustainable. So sustainable, there is a sustainability in the nano fertilizers. Everything is positive in the case of nano fertilizers. Enhance soil biological health, more microbial diversity, enhance native nutrient mobilization, and reduce the demand of fertilizers because you don't need much fertilizers for the crops. So you can use these type of nano fertilizers. So it's very appealing to use this. So like I said, every fertilizer has its disadvantage. What is the nano fertilizer disadvantage is that it's a waste toxic material. Because these are very small sized nanoparticles, very small size. So they can actually go into the body. People who are working with agriculture, So they can go enter into the body. They can enter into the soil very well. They can enter into the even water very easily, and then they contaminate. So they become a kind of a toxic materials. But there has been a lot of
Hello, sir. Your voice
sir.
is not audible.
Then the sir, oh sorry, can I now?
Yes, sir. Yes, sir.
Okay, so sometimes what happens is that they cause the respiratory disorder. This is something unusual with the nano fertilizers. Other fertilizers don't use respiratory. They cut is given through the nasal vessel, and then probably they enter into the lungs. So they actually lead to be respiratory disorder. Particularly, they're very light, so they actually enter the body with these problems. So they enter the body, they actually causes the problem with the carcinogen, like cancer causing. So they can be really problem with the cancer. That has been found. But again, it is not very discouraging because very few people actually have been faced these problems compared to the general. Yeah, it is not a general statement that I'm making. So there are some ill effect as well, like there will be toxic layer. There are people actually come up with so many things. But there are definitely cons with the nanotechnology. Like every system has a advantage and a disadvantage. Every system, irrespective of what system you are in, both it has a good things and the bad things. Like that, nanotechnology is a good things. Instead of curbing that cons of nanotechnology, we should increase the uh, we should decrease the cons and increase the effectivity. That would be the only solution that we can actually come across. So there, no problem. That cons can be actually, uh, uh, addressed. Obviously, one or other day we can address, and then we can make it more efficient. So what I want to say is that finally, the nanofertilizers have the potential to increase the crop productivity through the slow and controlled delivery. And due to their small size and high large surface area, and then they have a target specificity, high efficiency, they can be applied into the nanoparticle form. Then that also it may reduce the ill effects, particularly environmental or ecological problems that can be minimized using the nanoparticles. So future looks very bright for the nanoparticles because a lot of people are working. That is a very encouraging, because they will come up with someone will come up with some idea which can really address the problem. So there is understanding the future is that we should understand nanoparticles in a better way, produce them in a better way, in a bulk way, so that we can use these nanoparticles in a many aspects, including the nanofertilizers. So again, we should actually address the issues, which is a toxicity, which is a carcinogen effect. So if we can address this, it definitely becomes a future thing about the nanofertilizers. So nanofertilizers, in a time frame, definitely they will be replacing the complete conventional organic and also bulk fertilizers, and then they will roll the nano fertilizers completely. So we for the need of an hour is to address the problems that with the nanotechnology that has, and if you can do that, if the people coming, the young generation, if you can come into this field, and then if they do that, it will be definitely one of the great advantages. So there is a potential application of nanotechnology in agriculture. I think everybody is actually doing with every agriculture university in the world is working with the nanoparticles to make that potential application with the nanotechnology. I took long time, I guess, and I hope I made some sense of this nanofertilizers. Hopefully, you may have some questions, but I'm ready to answer. Definitely, there's no doubt. And I really thank once again Veeresh Magala sir, and then Tontadarya College for giving me opportunity to express my views on the nanofertilizers. And hopefully, I believe that some of the things that I said make sense. Thank you very much for your kind attention. Thank you all. Thank you, sir. Yes, if you are shy enough to ask the questions, so you can actually approach me in the email ID that I will be giving to the organizers. You can actually write to me. That's not a problem with your clarifications or questions. That is not our issue. Yes. Sir. Thank you, sir. Thank you, sir. Thanks. Yes. 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 Yes, sir. Yes. Oh, thank you. Thank you. Sir. It's my pleasure. Thank you. Thank you. Thank you, sir. Thank you. Oh, so nice, sir. So nice. Thank you very much, sir. Thank you very much for giving me an opportunity. Thank you. Thank you. Bye. Sir. Okay, sure.
Hello, am I audible, sir?
Yes, madam.
Yes, madam. Yes, madam.
Good afternoon, everyone. Respected Principal, Dr. M. Maruti, sir, HOD of Basic Science, Professor Sunil S. Patil, sir, Dean R&D, Dr. V.T. Magras, sir, our most valued invited guest, Dr. P.M. Gururaj, sir, and all the participants of today's FDP and staff members of Basic Science. It's my privilege to propose vote of thanks on this occasion. I, on behalf of Principal, HOD, staff members of Basic Science, a very hearty vote of thanks to the speaker, Dr. P.M. Gururaj, sir, for gracing your important work towards a perspective on nano fertilizers and sustainable agriculture and sharing with us a very important aspect. Thank you, sir. Thank you for your intellectual talk.
Thank you.
I would like to thank you, sir. And I would like to thank Principal, HOD, and Dr. V.T. Magras, sir, for their guidance in completing the task. And finally, I thank convener Professor Madhu K.N. sir and everyone enough for their involvement and I thank all the participants for their interested involvement. Thank you, one and all.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.
Thank you, Gururaj, sir.
Sir. Bye, sir. Bye.
Yes, sir. I am here. Just Okay.
Yes, sir. Yes, sir.
Hello.
Dear participant, the second session will be start very soon, and to that our resource person is Professor Sushil G. Adur, Department of Chemistry, Govindaram Seksaria Science College, Belagavi. Before that, I would like to uh, give our Jyoti Reddy ma'am to introduce our today's resource person.
Good afternoon, sir.
Uh,
Good afternoon to everyone. It is immense pleasure to me to introduce our resource person, Dr. Sushil Kumar G. Adur, Assistant Professor in Chemistry, Govinda Saria Science College, Belagavi. He has completed his Master's in Physical Chemistry in 2003 from Karnataka University, Dharwad, and he completed his PhD in polymeric membranes for liquid-liquid separation under the guidance of Dr. Lata S. Manjeshwar, Madam. And also, Sir has published 7 papers in peer-reviewed international journals and 2 papers in conferences. Sir has started his career in 2018 as an assistant professor at Govinda Rama Seksaria Science College, Belgaum. And also, Sir has completed his DSc project on designing of a novel modified polymeric membranes for pre-evaporation separation of water organic mixture of a grant of 24.3 lakhs rupees. And Sir served in a many field. Among them, I am sharing only few here. Sir is organizing secretary for national seminar on the scope of material science held in March 2017 at GSS College, Belgaum, and national seminar on global warming reason, challenges and solutions held in March 2019 at GSS College, Belgaum. And Sir has many responsibilities, among them very few here. He is a UGC coordinator, RSUA coordinator, member, core committee for autonomous state planning. Sir, I welcome you to in this seminar, sir. Thank you to giving me this
Thank you,
opportunity
madam.
to introduce the guest. Thank you, sir.
Thank you, Jyoti ma'am. Now I request our today's resource person, Professor Sushil G. Adur, to gather to inform whatever the deliver of today's topic to our participant. Over to you, sir.
Thank you, sir. And thank you, madam, for those kind words for the introduction. Hello, everyone. I am giving a talk on polymeric materials as membranes in evaporation separation. This is my today's topic on which I'm going to talk. So we are taking polymeric materials and we are considering them as membranes. I will talk on this as I go further. And we are using those membranes in evaporation separation. I don't know many of you whether you know this process of separation or not. So I will introduce this process to you first. Evaporation, it is a short form of permeation and evaporation. So what we are doing in evaporation actually is we are using the membranes, polymer membranes, and we are separating liquid mixtures. So that is done by a process called as evaporation separation. So there are many separation techniques involved. We know that one of them is evaporation separation. Others are like ultrafiltration, nanofiltration, reverse osmosis. All these things also we know. This is one of the techniques called evaporation separation. Pervaporation separation can be done for organic liquid mixtures or organic aqueous liquid mixtures. My specialization is in organic aqueous mixtures. When water is in small quantity in organic mixture with water, how to separate? It is not possible by other separation techniques when water is in very trace content. Like if I want a dry solvent, but if that solvent contains a very small amount of water, then it becomes difficult to separate that water and get the dry solvent. In that aspect, we have to apply pervaporation separation. Pervaporation separation works efficiently when water content is very less in the mixture. So I am talking mainly here about water separation in organic aqueous or organic water mixture. So we'll be seeing one by one how. So what is pervaporation? We usually call it as PV in the short form. So pervaporation is a process in which aqueous organic or organic liquid mixtures can be separated using a dense membrane or a porous membrane. Now we have to understand what is this dense membrane or a porous membrane. Whenever we use a polymeric material will be dense. So polymeric material membranes are always called as dense membranes. Then which are the porous membranes? Porous membranes usually are directly the inorganic materials which we use and prepare the membrane. There we are not using any polymer. So there, like zeolites, clays, these all can be prepared as membranes, but it is very difficult directly to prepare a zeolite membrane. So now in a zeolite membrane, the zeolites will be having the pores. So therefore, those such types of membranes where directly pores are available are called as porous membranes. Whereas when we consider the polymeric membranes, in polymeric membranes, we don't have the pores directly. Some people think that polymers will be having pores. Pores won't be there in polymers. Polymers will be having voids. So those voids will be exploited to separate water in organic aqueous mixture. So therefore, polymer itself is considered as a dense material, which will be having the voids. Therefore, polymeric membranes are called as dense membranes, and zeolite or any other inorganic material membrane, if you prepare, that is called as a porous membrane. So this is the major difference between a dense membrane and a porous membrane. Polymeric membranes will be always a dense membrane, not a porous membrane. So therefore, in pervaporation, we are using a dense polymeric membrane, and then it is a flat membrane. So that membrane will be utilized to separate aqueous organic mixtures. So I want water separated from aqueous organic mixture. So how to do that? That we'll be discussing throughout this session. So I'll be using pervaporation as my tool to separate water from aqueous organic mixtures using a dense polymeric membrane. However, that will be modified later. How to modify that also I will be discussing. So now if we check, okay. So this is the next slide which I am using to show you how the pervaporation setup looks like. So you can check here. Just a minute. Okay. So you can check here. This is the whole setup of pervaporation. It is of stainless steel. First upper part is called as feed chamber and lower part is called as permeate chamber. In between we are having this black strip, you can see this is our membrane. So it is a flat sheet membrane which we'll be using in such setups. So a flat, because there are two types of membranes which can be prepared. One is a flat polymeric membrane, another one may be a tubular membrane. For tubular membranes, the setup will be different. Usually in pervaporation, we don't use tubular membranes. Tubular membranes are usually used in reverse osmosis, nanofiltration, ultrafiltration. There we use the tubular membranes. In tubular membranes, membrane will be wound in a tube-like structure in many layers. So what happens in reverse osmosis, if you take, in reverse osmosis, water will pass from one end and it will pass through all the layers and it comes out from permeate end. So in between, the membrane will take up all the unwanted material and fresh water will come from the other end. So that is the tubular membrane. But in pervaporation here, we are not using tubular membranes. We are using flat sheet membrane. It will be a flat membrane which will be separating the aqueous organic mixtures. So now if we see this setup, as I said, now the upper part will be the feed part. We call it as feed mixture. The aqueous organic mixture is called as a feed mixture, and lower part will be the permeate part. So now in the upper part, which is the feed mixture, there we are taking aqueous organic mixture. Maybe because it is a lab setup, we are using 100 cc or 100 grams of feed mixture. Depending upon how much I am separating water and all those things, we are making the compositions like 10% water, 2% water, 5% water, and I'll be checking whether I can separate all the water from that mixture. So we can do pervaporation at, oh, sorry. Sir, hello. Hello. Sir, it went no somewhere. My presentation. Just a minute. Suddenly, shall I upload, sir? Should I upload it again, sir? Okay. But I'm not seeing presentation. Once again, should I upload? Oh, wait. I'm uploading, sir, again. No, it is uploaded now. Shall I continue? Yeah. Okay, I will continue from here. Right. So I was discussing about pervaporation setup. The upper part is the feed mixture part, and the lower part is the permeate part. And already I was discussing about the feed mixture part. So because I am doing aqueous organic separation, I am separating water. I'll be taking aqueous organic mixture at the feed part because it is a laboratory setup. It is not at the plant. It is at the laboratory setup. Therefore, we are taking around 100 grams of the mixture, like only 5% of water in that or 10% of water in that, something like that. And then we will be separating that water from that aqueous organic mixture. Usually alcohol separation and other separations can be easily done using pervaporation setup. So the upper part will be having a stirrer and also a thermometer. Stirrer, continuously it will be working to stir the mixture so that it becomes a homogeneous mixture. and then we separate water from aqueous organic mixture. And there is a thermometer also to check the temperature, because we can do pervaporation separation at different temperatures like 30, 40, 50, 60, even 70, 80 degrees we can do. There is absolutely no problem. Anything above 70, 80 degrees, it sometimes becomes difficult depending upon what is the glass transition temperature of polymer, because the glass transition temperature of the polymer is very important. If we cross glass transition temperature of the polymer, then it becomes difficult for membrane to withstand the water or aqueous water organic mixture. Therefore, below glass transition temperature, we have to perform pervaporation setup. Like PVA membranes, if you take PVA membrane, PVA is having a glass transition temperature of 95 degrees Celsius. So if I want to do around 100 degrees or 110 degrees, it becomes difficult, because what is glass transition temperature? At glass transition temperature, the atoms start vibrating in polymer. So at that point, it becomes difficult for the polymer to sustain the aqueous organic mixture, because the temperature is very high. Therefore, we cannot cross that. So anything below glass transition temperature is very fine. There is absolutely no problem. Therefore, to check the temperature, we are having a thermometer here and the stirrer to stir the aqueous organic mixture. Then we have got this membrane here on the steel plate. So this membrane will now help us to separate water from aqueous organic mixture. Get collected in this permeate chamber. So this permeate chamber is connected with a vacuum pump. You can see at the bottom here, there is a vacuum pump here. This vacuum pump is connected to permeate chamber. So otherwise, it becomes difficult to take out the permeate from feed organic mixture from the polymer membrane. So we need a vacuum pump so that it can suck that permeate into permeate chamber. And then further, that permeate will be collected. You can see these 3 tubes here. 3 tubes, glass tubes here. These glass vessels will collect, one of these glass vessels will collect that permeate. And permeate, one thing we have to remember, permeate comes in the form of vapor. So that's why the name pervaporation, permeation and evaporation, both the processes. So the permeate comes into this and then collects into this glass tube. Then it is in vapor form. Therefore, permeation and evaporation. Therefore, it is called as pervaporation. Now, how to take out this vapor form? Because we need water, but how to take out this vapor form? So because of that, we have to apply some dry ice or liquid nitrogen, because we have to condense that vapor back into water. So how to condense? Because at regular temperatures, we cannot do that. Therefore, what we'll be doing, we'll be applying to the glass tube a liquid nitrogen, usually liquid nitrogen, because liquid nitrogen will be at around -50, -70 degrees Celsius. Therefore, it can easily condense the vapor back into liquid form. So we can get water into liquid form. So this is how the whole setup looks like. Once again, I'll just tell, this is the feed chamber, and this is the permeate chamber. In between, we are having this black strip, you can see, that is our polymeric membrane. So this polymeric membrane will separate water from organic mixture, aqueous organic mixture. That will be collected in permeate chamber. Permeate chamber is connected with a vacuum pump. So that will suck. And therefore, because it is vacuum pump, it will come in terms of vapors. These glass traps here, this glass trap will be having liquid nitrogen below that in a flask. That will condense that vapor back into its liquid form. So this is how the whole idea of pervaporation works. And then that glass trap will be taken out, and that will be measured for different aspects. Now, if we see the next setup, why pervaporation? PV is pervaporation. Why we need pervaporation? Because we are having distillation also, we are having any other process also to separate water or separate organic mixtures. Then why do we go for pervaporation? So these are the important points for why we go for pervaporation. Important aspect is separation of azeotropic mixtures. We know what is an azeotropic mixture. This is a mixture at a certain level where both the liquids become identical in their nature, and it becomes very, very difficult to separate those mixtures. So in that way, we need some process where we can separate one of the liquids from that mixture. So which one we have to use? The best method used is evaporation, because other processes, although some of them can be used, but there are issues involved in other processes. Like another one is separation of close boiling mixtures. So these can be done using evaporation. What is the problem with other processes like distillation if we are using? So third one I am saying, in evaporation we need less energy compared to distillation. Distillation needs higher energy, but evaporation needs quite lower energy compared to even distillation or any other process. So therefore, especially for azeotropic mixtures, evaporation is the best way. Or as I told, when water acts as a very small or trace content in organic solvent, then only evaporation is the best way to separate water from organic. And also ease of operation. The fourth reason for using evaporation is the ease of its operation. As we have seen here, it is very easy to set up also. It is very easy. Evaporation setup is quite easily done, and we can easily set it up and we can easily work. Therefore, ease of operation is the next reason why we can go for evaporation. And next one is environmentally benign. This is quite environmentally benign, environmentally friendly, or we can call it as eco-friendly, as there is no any harmful chemical is involved in this. This is quite environmentally benign. The next one, that's what I am given. No carcinogen is involved. So therefore, this whole setup, the whole process is environmentally friendly or eco-friendly, we can call. So the important mixtures which we can separate are azeotropic mixtures, close boiling mixtures, and when water acts as a trace in the organic solvent, then we can use evaporation using membrane. The very efficient technique to be used. Now, which are the polymers which can be used in evaporation separation? So I have just given here a few of the polymers which are widely used throughout the world, like polyvinyl alcohol. I have separated them as hydrophilic polymers and hydrophobic polymers. And when it comes to hydrophilic polymers, I am interested in hydrophilic polymers because I am separating water. So if I use hydrophobic polymer to separate water, it is impossible because it will not attract water. We need a polymer which can attract water. Therefore, we must use hydrophilic polymers to separate water from organic aqueous mixture. Because of this reason, there are three important polymers which researchers use widely throughout the world. First one is obviously polyvinyl alcohol, or we simply call it as PVA. It is a synthetic polymer. We all know this. It is not a natural polymer. It is a synthetic polymer, and it can be easily used in evaporation. So PVA, once again, we know it is a versatile polymer. It can be used in scientific research. It can be used in engineering, or even it can be used in medicine also. So we have seen the versatile utility of polyvinyl alcohol everywhere throughout the world. Therefore, researchers usually rely upon polyvinyl alcohol as the base polymer, and then they develop polyvinyl alcohol into whatever they want. Therefore, it is one of the versatile polymers which we use in evaporation also. Then comes sodium alginate. Sodium alginate is a polysaccharide. This is also once again very fantastic hydrophilic polymer. Even in our lab, we have used extensively sodium alginate to separate water from aqueous organic mixture. It works next to PVA, we can call. And its separation factor is also very good in comparison with PVA. It also gives a very good separation to water. So therefore, it is one of the important natural polymers. It is a natural polymer. It is not a synthetic polymer. It is a natural polysaccharide, which it is alginic acid initially. Then it will be converted into the salt of alginic acid. So sodium salt. Then it becomes sodium alginate. Initially, it will be alginic acid. It's in original form. Then, because in alginic acid, we cannot directly make a polymer out of that. So polymeric membrane. alginic acid will be converted into sodium alginate, a sodium salt of alginic acid. Then it becomes sodium alginate. Then only it can be used as a membrane for separation of water. And third one, which usually people use, is chitosan. Chitin is its original form once again, and it will be converted into chitosan. Then only it becomes, it can be used as a polymeric membrane. It is a carbohydrate polymer once again. So these are some three of the important polymers which usually researchers use for their work. Okay. Now we'll see what are the advantages of these hydrophilic polymers for water separation. Why should we go for these important polymers? First, if we see PVA, and as already I have seen, it has got a fantastic hydrophilic nature. Without that, we cannot achieve any water separation. So therefore, the first reason why we can go for PVA is its good hydrophilic nature. And second one is because it is very hydrophilic in nature, its perm selectivity, we call it as perm selectivity because of permeation. So it is a technical word, perm selectivity. So perm selectivity to water, what is that? To separate water using membrane. That is called as perm selectivity. So perm selectivity to water is very high. So therefore, this is important factor for us because we are separating water. High perm selectivity to water is one of the advantages why we go for PVA membranes. Next is chemical resistance. This is very important because we can separate many organics using PVA membrane. If it is not resistant to the chemicals, then it becomes difficult. Then it ruptures in between in the process itself. So if it happens, then there is no use. Therefore, PVA, when we take, PVA is very quite chemical resistant. Therefore, we use PVA. And next one is film forming ability or membrane forming ability. It has got a fantastic film forming ability. I will show it later, the membrane. The film forming ability for PVA is excellent compared to any other hydrophilic polymer. Therefore, this is one of the better candidates for pervaporation. And lastly, it's TG and TM. I have already discussed it earlier. What is TG? TG is glass transition temperature. And what is TM? TM is melting temperature of the polymer. So TG, when it comes, glass transition temperature, as I discussed earlier, glass transition temperature is a temperature at which the atoms in the polymer start vibrating. Once they start vibrating, the issue is at that temperature, for pervaporation, it becomes difficult crossing that temperature because atoms will leave their place and they will be misplaced. Because of that, the voids present, they will lose their structure. Once they lose their structure, voids in the polymer, if they lose their structure, then the separation becomes difficult. Suppose if voids get opened, then even organic will come into the void and permeate will get organic also, which we don't want. So therefore, when we take PVA, its TG is very good. As I told, it is 95 degrees Celsius. Therefore, we can work very well with PVA. And TM, TM is the next one. After TG, we get TM, that is melting temperature. Melting temperature for PVA is around, I think, 180 or 190 degrees. Therefore, we have got a huge working space for PVA with respect to TG and TM. Coming to sodium alginate, once again, it is also highly hydrophilic in nature. Because it is hydrophilic, as I told, its perm selectivity to water is also very good. Once again, this is also highly chemically resistant. And once again, its film forming ability is also excellent, just like PVA. And chitosan also, all these characters hold good for chitosan also. Of course, I have given only good hydrophilicity, but even the other things also hold good for chitosan also. Because of these excellent advantages, we use these three polymers for separation of water in aqueous organic mixture. Coming to hydrophobic polymers, of course, I am not discussing much about hydrophobic polymers because my today's talk is only for separation of water using polymeric membranes. Therefore, I am discussing mainly on hydrophilic polymers, not on hydrophobic. But hydrophobic polymers, once we consider like PDMS, polydimethylsiloxane, polysulfone, and polyether ether ketone are best polymers for organic separation. If I am separating organic solvent from organic mixture, then these are good polymers to separate organic. However, we see that later I'll be using polyether ether ketone, but I'll modify it and use it as hydrophilic polymer. That is the beauty of polyether ether ketone. We'll discuss it later. So polyether ether ketone can be converted as a hydrophilic polymer also, although it is basically hydrophobic polymer. This also we'll discuss just a few moments later. Okay, I hope you can see this picture. This is a typical PVA membrane. This is the paper on which I have kept a round-shaped polymeric membranes. This polymeric membrane is of PVA, polyvinyl alcohol. So you can see that polyvinyl alcohol membranes are always quite transparent. They won't be opaque in nature. They are quite transparent. It's just like a transparent plastic. So PVA is a semi-crystalline polymer, and it is readily soluble in water. Sometimes we have to give some temperature like 40 degrees Celsius or 50 degrees Celsius. Around that temperature, it easily gets dissolved in water. And then if we form the film, we get such fine film of 40 to 50 microns. In pervaporation, we use 40 to 50 microns thick membrane. We can control the thickness of membrane. So this is a typical PVA membrane which is used in pervaporation separation. Okay, now coming to the technique, how the process takes place in pervaporation. So PV separation mechanism through a dense polymeric membrane. First, we'll discuss about polymeric membrane. However, always it is dense polymeric membrane only, and then we'll go for porous membrane. So here, this is the membrane where diffusion is written. Of course, I have taken it vertically, but as we have seen in the setup, the membrane will be kept horizontally, not vertically. That we should understand. However, just for clarification, I have shown it in vertical nature, but membrane will never be kept in vertical nature. We need to understand that it will be always horizontal between feed chamber and permeate chamber. So this side, now sorption side, whatever I am saying, this is feed side, and permeation side, whatever I will be saying, that will be for permeate chamber. In between diffusion side, whatever you are saying now, diffusion side will be the membrane. So now these are the three important aspects of pervaporation: sorption, diffusion, and permeation. Permeation, however, in terms of evaporation. So these are three important aspects of any pervaporation technique: sorption, diffusion, and then permeation. Now what happens at sorption side, that we'll see. So once we are having aqueous organic mixture here, that will be kept on the upper part of polymer membrane. So now water and organic are in contact with this membrane. We have to keep it around 2 hours, and it will be sorbed. The polymeric membrane will be sorbed. That is the sorption. Without sorption, there is no diffusion. That we need to understand. Once it sorbs, then only there will be a diffusion. So what happens here? The important part for pervaporation separation using polymers is that it must swell. If it doesn't swell, then there is no separation. The polymer must swell. Why it should swell? Because it should give the voids. Voids will be very narrow initially without any sorption. Once the polymer gets sorbed with water, then what will happen? Because it is hydrophilic polymer, the hydrophilic polymer will swell. So once it swells, the voids will get opened in the polymer. So that through that void, the water can easily come into polymer. So this is the sorption part. So in sorption part, the polymeric membrane will be sorbed and it gets swollen. So once it gets swollen, the voids will get opened and water will go through into those voids and diffusion will take place into the polymer. So sorption, then diffusion. Diffusion of water into polymer, then it's permeation from another end. Then it will come into permeate chamber. So that is permeation. Permeation in the form of vapor, not directly in the form of liquid. It will be in the form of vapor. So permeation, sorption, then diffusion, then permeation. So these are important aspects of any pervaporation using polymeric membrane. So once it comes into permeate chamber, it will be in the form of vapor. This I have already discussed. Then it will come into the glass trap, and there it will be condensed by liquid nitrogen back into liquid form, liquid water. So this T is thickness of the membrane. This will be using into calculation later. So these are the three important issues of pervaporation. Okay. Next one is pervaporation through pore flow model. This is the one which I was talking. Dense membrane is over using polymeric membrane. This is using any membrane which are having pores, usually zeolite membranes. If we are casting directly zeolite membranes will be having pores. Zeolites won't be having voids. Polymers will be having voids. Zeolites will be, or any other inorganic material, if you are making any membrane, those inorganic materials will give you pores. Through those pores, water will flow. So this is upper part, feed part, and this is the membrane having pores. Different pores will be there. Through those pores, water will flow and it gets diffused, and then it will come out into permeate chamber. So once again, sorption, diffusion, and permeation will be there, but it is in a different way. So in this way, the pores will play the act. There it was voids in the polymer. Here it is pores. Through pores, water will come into the membrane and it will go into permeate side. So these are two important theories for any pervaporation: sorption, diffusion, and permeation in dense membrane and in porous membrane. Okay, now we'll see which are some important parameters which can be studied using pervaporation, and why should we study these parameters. Two important aspects for pervaporation which will be studied by anybody will be flux and separation factor. What is the meaning of flux and what is the meaning of separation factor, that will be seen. Flux is J equal to W by AT. W is weight of the liquid which is permeated in terms of kgs. A is area of the membrane used in meter square, and time in terms of hour. So J gives flux. It is a quantitative approach. How much water has been collected quantitatively, that we can see. So it is kg per meter square hour. So it comes, the units used are kg per meter square hour. So it gives a quantitative approach, how much water has been collected in permeate side. And then separation factor. Separation factor is unitless. We should understand this. It is unitless, but it is a qualitative approach. What is the content of water in permeate? It is a qualitative approach. You can see it is given by alpha equal to PA upon 1 minus PA into 1 minus FA divided by FA. So PA and FA are water contents in feed and permeate. Okay. Next is pervaporation separation index, or simply we to alpha minus 1. J is flux into separation factor minus 1 will give us PSI. It is quantitative approach. Enrichment factor. It is also a quantitative approach. CWP divided by CWF. C is concentration of water. CW is concentration of water. P and F are permeate and feed. So these are four important factors which we study using pervaporation. Then coming to the membranes, again, polymer membranes. Although we say that polymeric membranes are quite efficient in separating water from aqueous organic mixture, however, there are some drawbacks associated with polymeric membranes. What are those drawbacks? We'll see. There are three important drawbacks which I have quoted here. Excessive swelling, lower mechanical strength, and cyclic utilization not possible. What are these things? Excessive swelling. As I told, if there is no swelling, if I go back earlier slide. Okay, here I told the polymer must swell. Without swelling, there is no diffusion. But how much it should swell? If it swells to higher extent, then also it is problematic. What will happen if it swells more? So if it swells more, the voids will get opened more. And because of that, the size of void will be more. And then water and organic both will come into the void and both will be diffused and both will get collected into permeate. That's what we don't want to happen, as we need only water to be separated. If water only has to be separated, then void size must be controlled. How to control void size? We have to decrease the excessive swelling happening in the polymer. If it swells excessive, then both will come, because we need size discrimination here. So it is called a size exclusion. So if there is no size exclusion, then there is problem. If we see, suppose if I am separating water and isopropanol, water and isopropanol sizes are different. Isopropanol will be bigger, water will be smaller. So water comes easily if the size of the void is smaller. What will happen if size of the void is more? Then even isopropanol will come into the permeate. So if there is excessive swelling of the polymer, then it becomes difficult. And most of the polymers swell excessively in presence of water. So we need to avoid that problem. So this is one of the major drawbacks of the present polymeric membranes: excessive swelling. Then lower mechanical strength. And this is another important aspect. If mechanical strength is lesser, then what happens? Then it may rupture. The polymeric membrane may rupture during the process. Therefore, we need good mechanical strength for the polymer. So in the in a pristine state of the polymer, its mechanical strength will be lesser compared to modified polymer. We'll talk about modified polymers later. So lower mechanical strength is another problem associated with polymeric membranes. Why lower mechanical strength? Because of the entangled structure of the polymer. So once the structure is, because polymer chains, we all know, this is a macromolecule and it cannot sustain its backbone. So once it cannot sustain its backbone because of long polymeric chains, it will get entangled. And once it gets entangled, its mechanical strength will be lesser. So that is another problem: excessive swelling and then lower mechanical strength. Therefore, because of these issues, cyclic utilization is not possible. What is cyclic utilization? The number of cycles how I can use the polymeric membrane. Suppose for one process I have used same membrane, whether I can use it for multiple uses, for next use also, for 10th use also, whether it is possible. So that is not possible if I am using pristine polymeric membrane. So these are three important drawbacks associated with any polymeric membrane. So what should we do to improve the membrane performance? How to improve the membrane performance? I have quoted here a few of the important things how we can improve polymeric membrane performance. First one is cross-linking by a suitable agent. Without cross-linking, it is almost impossible to use any polymeric membrane in pervaporation separation. How to cross-link? Cross-link, usually urea formaldehyde we use, or glutaraldehyde, usually aldehydes we are using to cross-link the membrane. Once membrane is casted, then it will be cross-linked with any suitable agent. Then second one is blending with another suitable polymer. So we can blend two of the polymers in different ratios to increase its mechanical strength and also increase its suitability for our aqueous separation. Third one is grafting. Grafting of two polymers also can be done, or this one we are talking now. Nowadays we use these techniques very much. Incorporation of fillers. Usually the inorganic substances like zeolites, clays, mesoporous and microporous materials, and heteropolyacids. In this talk, I am going to give you heteropolyacids. How I have used heteropolyacids, like modified heteropolyacids, to improve membrane performance. And also earlier I have used inorganic substances like zeolites, clays. These also work very well, especially clays and zeolites. Even mesoporous also people have used. And but in today's talk, I am concentrating only on heteropolyacids. Okay, so we'll see the mechanism for mixed matrix membrane. There are two different types of membranes how we can get the membrane. So now I am introducing heterofolate acid into any polymeric membrane, and how it works I am seeing. So such membranes wherein inorganic fillers are mixed with polymers or incorporated with the polymers are called as mixed matrix membranes. These are always called as mixed matrix membranes. So how do I get mixed matrix membrane? Suppose these are heteropolyacid particles. I have just given it schematically. Suppose these are heteropolyacids or zeolites, I have told. And if this is my polymeric matrix, now if I can fix these heteropolyacids into polymeric material, then I get a mixed matrix membrane. How does it look? So if I can put these fillers, I hope you can see this. If I put these heteropolyacid particles into the polymeric matrix like this, then I get a mixed matrix membrane like this. So yellow circles, schematically I have shown them as heteropolyacids, and the matrix is of polymer. So now it becomes a mixed matrix membrane. This is one of the technique how I can get a polymeric matrix. There is another one. If I am using clays usually will be in terms of layers. If they are in terms of layers, then I don't get a mixed matrix membrane. In that way, I am getting an intercalated structure. Then it cannot be called as mixed matrix membrane. Mixed matrix membrane I can say only when the particles go and sit into the polymeric matrix. Then it is called as a mixed matrix membrane. But however, if the filler is in terms of layer, then I cannot call it as a mixed matrix membrane. Then I have to call it as an intercalated structure. Then what will happen? Okay, suppose this is a clay structure. I have once again schematically I have shown. Suppose these are different layers, and if this is the polymer also we know that polymer chains will be there. Then if I can fix those layers into polymer chains, then what will happen? So these are polymer chains. Sorry, this is the clay structure, and these are polymer chains. So if polymer chains are made to sit in between these clays, then I get just beautiful structure like this, which is called as intercalated structure. So now this is because of using a clay. But here we are discussing only about mixed matrix membranes. Okay, now I'll be taking two of my works, and then I will discuss how we separate water using a mixed matrix membrane. So first one I am using is mixed matrix nanocomposite membranes. We call them as NCMs. Nanocomposite membranes, NCMs, mixed matrix NCMs of sodium alginate. Already I have told so about sodium alginate with modified phosphotungstic acid. What is modified phosphotungstic acid? After a few moments, I'll come to it. So how to prepare a mixed matrix membrane using MPTA? MPTA is modified phosphotungstic acid. So here what I have done, I have incorporated 3, 5, 7 and 10 weight % of PTA as well as MPT to check what is the difference if I have not modified PTA, and what is the difference when I have when I have modified PTA. What is the difference in separation factor and flux? This I am studying. General formula for Kagan type, this is called as Kagan type heteropolyacid. You can check it in my paper. What is Kagan type? You will come to know. Paper I have given here, separation and purification technology. You can go through. At the bottom I have given volume and everything. Separation and purification technology. If you check there, you will come to know what is Kagan type heteropolyacid. And the general formula for Kagan type heteropolyacid is HNX M12O40. This is the general formula. However, for PT I have given it is H3PW12O40. So M and O will be constant. H and this metal will be changing. H number of protons and the metal will be changing. So here it is PTA, phosphotungstic acid. And this we have used for separation of isopropanol and ethanol. Why should we go for modification of PTA? So modification of PTA I have given. First we see how do we modify PTA. Phosphotastic acid is treated with ammonium carbonate. Why do we use ammonium carbonate? Ammonium carbonate will give us NH4 plus ions. NH4 plus ions, we all know that NH4 plus ions are bigger in size compared to proton. If protons are more, then what will happen? It will allow the phosphotungstic acid to become more hydrophilic. Once again, we want to restrict hydrophilicity of PTA also. Now what we are doing? We are restricting the hydrophilicity of sodium alginate as well as PTA, both. So first we'll talk about modification of PTA. PTA, we are doing it with ammonium carbonate, NH4 plus. Separate solutions of PTA and ammonium carbonate will be done, and then both will be mixed. And then the white, super white solid what comes out will be dried up in hot oven. Why modification of PTA? This is very important. I can directly use the heteropolyacid, phosphotungstic acid in sodium alginate, but why do we go for modification of PTA? This is very important. Once again, excessive protons, there are 4 important reasons here. Excessive protons present in PTA will make the PTA to leach out. This is very important. If I directly use PTA, some researchers earlier have used PTA and they have struggled. Directly they have used the PTA into sodium alginate or PVA. What will happen if I don't modify, if I don't restrict protons present in PTA, then what will happen? It will leach out from the membrane, because we are introducing PTA into sodium alginate. So once it becomes a mixed matrix membrane, and then when we use for pervaporation, but if I go for higher water concentration or higher temperature, the PTA will start coming out of the membrane, and obviously the membrane will not work. So if I don't modify, protons will make a foul play in the separation process. Therefore, we have to restrict. We must restrict the protons. How to restrict protons? Introducing higher ionic size, another one, and separating proton and introducing that higher size ion, positive ion, like NH4 plus we are introducing here with ammonium carbonate. So to increase the mechanical strength, if I restrict these protons, I have given earlier the structure. Just a minute. Okay. So earlier Kagan's type structure I have given. If you remember, H proton must be controlled there. The number of protons, if they increase, the leaching out problem will increase. So how to restrict that? With ammonium carbonate, which will increase also the mechanical strength. So at higher concentration of water also it will work very well. And to increase the overall performance of the mixed matrix membrane. So once we control these protons, then overall performance also will increase, and separation factor and flux will increase. We see that in the process later, the separation factor has increased very well for the membranes with MPTA. And only with PTA also I have given the difference, we can check later. And cyclic utilization becomes easier. I have already told, only using polymeric membrane, it is not possible for cyclic utilization of the membrane. And if we incorporate such fillers, we can go for cyclic utilization. Then coming to membrane fabrication. Solution casting method. This is called as solution casting method for a flat membrane. So what I do here, I have taken 4 grams of sodium alginate in distilled water, 80 ml of distilled water or deionized water. And as I have told, 3, 5, 7, and 10 weight % of PTA and MPTA are incorporated. So 3% of 4 gram will be 0.12, and then 5% will be 0.2, 0.7 will be 0.28, and 10 will be 0.4 grams of PTA. Will dissolve in 20 ml. Separately, they are stirred, and then PTA solution is incorporated into sodium alginate solution. Solution was casted, and then once again for 24 hours it was stirred, and once homogeneous solution is obtained, that solution was casted on a glass plate. The dried membranes then were immersed in cross. However, we go for filler addition, we have to go for cross-linking. Then cross-linking is done using glutaraldehyde here, and then washed continuously with water and the membrane is dried up. This is how we fabricate the membrane. So once membrane, this is a flat membrane. Once membrane is, hello. Okay. Stuck? No, I am seeing here, sir. Okay, I'll go back and come there. Droplets. There only it is stuck. Wait. Okay, I am here now. Major drawbacks. Just check, sir, whether now it came. Hello. Oh, how is it that? No, here it is showing no. It is going further. It is not going there. Hello. Okay, then what to do? I have to continue. Okay, just check mechanism of mixed matrix membrane. Is it there? Just check. Okay. Now intercalated structure. Oh, okay. Wait. Okay, now mixed matrix nanocomposite membranes of NCMs of sodium arginate. It is there. Modification of PTA. Why modification of PTA? Okay. Now I am here. Membrane fabrication. Okay. Thank you. So now we are at membrane fabrication. It is a flat membrane. So we are preparing at 3, 5, 7, and 10 weight% of PTA as well as MPTA, both, to check the difference. What happens when we use modified PTA? Okay, this is just a typical SEM image I have given of sodium. This is how it looks at atomic level. This is scanning electron microscopy image. It is called as SEM image of MPTA incorporated NaLG NCMs, nanocomposite membranes. So we have already incorporated modified PTA into sodium arginate, and then we have checked the SEM image. This is how the SEM image looks, and you can see those round structures which show that it is MPTA incorporated in sodium arginate. If you just check sodium arginate, there won't be any such distractions in sodium arginate. It will be just plain. If you check sodium arginate SEM image, so this shows clearly the homogeneous structure of MPTA incorporated into sodium arginate. This is atomic force microscopy, once again, to prove the homogeneous structure after incorporating MPTA into sodium arginate. So MPTA is incorporated into sodium arginate. The first structure, A structure, is only of sodium arginate. You can easily see the difference. Only a sodium arginate is not having any those granules-like structures. In B, you can check the granule-like structure, which shows that MPTA is incorporated into sodium arginate. However, in structure A, the AFM figure of A shows that there are no such granules. It is almost plain. So it is of sodium arginate. And next one, you can see the granule-like structure in sodium arginate. This granule-like structure is because of MPTA incorporation into sodium arginate. Therefore, it shows such granule-like structure. So we can easily prove that MPTA is homogeneously distributed in sodium arginate. Okay, so these are the PV data for water isopropanol. This membrane I have used for separation of water isopropanol as well as water ethanol. So water isopropanol mixture, if we see isotropic mixture, it forms at 12.5% of water with isopropanol. Here, as we have seen the pervaporation setup, in the pervaporation setup, we have kept PVA MPTA membrane, NaLG MPTA membrane, and we have separated water from water isopropanol mixture. Water isopropanol mixture will be at feed side, and the permeate side we get water. Then what will be the separation factor? So first one we can see in the table, pristine I have given. This is pristine NaLG without addition of PTA or MPTA. Separation is very less, 678, and flux is 0.065. Flux J kg per meter square over it is, and separation factor is unitless. PSI and beta are also unitless. This is 43 lesser, and this is 14. This is also lesser. For pristine, we can see that all the data are lesser. As I go on adding PTA into sodium arsenate, I see that my performance increases. So from 3, 5, 7, and 10, I see that all the separation factors are increasing. Accordingly, my flux values are also increasing. Many times what happens, flux decreases. But here we see that with incorporation of higher incorporation of PTA has resulted in higher performance. And then we see that as I add now MPTA, so MPTA is modified PTA with ammonium carbonate. Now what will happen? So because now I have added MPTA 3, 5, 7, and 10, you can see as I go on increasing MPTA, the performance of MPTA membranes compared to only PTA incorporated membranes are much higher. So why does it happen? This happens because we have modified the PTA. If I don't modify the PTA, then what happened? The PTA will leach out later. So because of that, the performance is lesser. But MPTA values, you can see, this is much higher for MPTA 10, 8591.316. So this is much higher because MPTA works much better because we have modified and removed the excessive protons and we have added NH4 plus ions. Because of that, we see that all the performances with MPTA are higher compared to PTA. So this is my first work which I wanted to discuss. Now, if we see for isopropanol, okay, this is for this is for ethanol. This is for isopropanol, and this is for ethanol. Sorry for the headline. Headline I have by mistake. It is water isopropanol. This is actually for water ethanol. So water ethanol mixture. Once we see the azeotrope concentration is very lesser for water ethanol. Water at 4% only it forms azeotrope. So it becomes very difficult to separate water. But using this membrane, we have separated water with water ethanol mixture also, although its azeotrope is very less. So pristine membrane, if I see, separation factor is very less. Why does it happen? Once again, because the azeotropic composition is very lesser for water ethanol compared to water isopropanol. Water isopropanol, as I told, at 12.5% of weight of water, it forms azeotrope. But for water ethanol, it forms only at 4%. Then you can imagine, at 4%, it becomes extremely difficult for any later compositions. If I go for 10 weight, 20 weight% of water, it becomes extremely difficult to separate water from water ethanol. So therefore, when I use pristine membrane for 10 weight% of water, separation factor is very less, 24, and flux is also very less, 0.039. Then I started using NaLG PTA3, PTA5, PTA7, and PTA10. I see that the performance increased when I added PTA. Further, and when I added MPTA, the performance further increased and it went up to 1866 for MPTA 10. So if I compare MPTA 10 and PTA 10, PTA 10 is 288 only, and MPTA 10 is 1866 for separation factor. So it clearly shows that modification has got value. If I don't modify my PTA, my performance levels will be very less. So it shows that, and it proves that I need to modify PTA or any heteropolyacid, then I incorporate it into polymer, then I use it for PV separation for better performance. This is my first work with NaLG. My second work, this is, I have already told, this I am using mixed matrix nanocomposite membranes of sulfonated polyether ether ketone. So once it is sulfonated, we call it as peak. Polyether ether ketone, already I have told, you must be remembering that it is a hydrophobic polymer, but its beauty is it can be converted into hydrophilic polymer also. So how to convert? We can sulfonate it, we can introduce sulfonic acid, and then we can make it sulfonated polyether ether ketone, then it gets converted into a hydrophilic polymer. That also we have used with modified silicotungstic acid. Earlier we have used phosphotungstic acid. Here we are using silicotungstic acid, depending upon the appropriate usage with the polymer. And here also we have incorporated 3, 5, 7, and 10 weight% of STA in speak. We have used it only for separation of isopropanol, and we have studied. And modification of STA, once again, the process of modification is entirely same, but we have used, instead of ammonium carbonate, we have used cesium carbonate here, because cesium carbonate is quite appropriate compared to ammonium carbonate. Therefore, we have used cesium carbonate. Cs plus ions will replace excessive protons, and then we get a modified STA, which is much stronger compared to just STA. Just STA, if we use once again, even in polyether ether ketone, it will leach out, and the membrane performance will be quite lesser. And the same process is involved for separation, for preparation of STA, modified STA. So why speak? This is important. Polyether ether ketone in its original form will be hydrophobic, but proper degree of sulfonation will make peak hydrophilic. It works fantastically, polyether ether ketone. Therefore, we have used this polymer for this work to separate isopropanol. We have used the commercially available 53% sulfonated peak. 53% sulfonated peak works very well. And the structure of peak I have given here. So if it is polyether ether ketone, then sulfonic acid group won't be there. Now it is sulfonated, therefore sulfonic acid group will be there. If it is not there, it is just peak. And if we introduce sulfonic acid, then it becomes sulfonated polyether ether ketone. We just simply call it as peak. This is the same image. Once again, the granule type structure will show you the MSTA incorporation into sulfonated polyether ether ketone. Without this, there won't be any granule type structure for sulfonated polyether ether ketone. If just a simple polyether ether ketone, if we see same image. Yeah, this is the 3D structure, fine structure of 3D AFM. Earlier, I had shown only a planar structure of AFM for NALG PTA membranes. But here I have shown the 3D structure. You can easily see here the crystallinity observed. The peaks you can observe every year. So those peaks are because of incorporation of MSTA. If I don't incorporate any filler there, there won't be any peaks available. It will be just a planar membrane. If it is only of peak or speak, it will be a planar membrane. But because we have incorporated a filler like modified STA, then we get those peaks, which shows the crystallinity. Crystallinity is very important in pervaporation separation. If it is not crystalline, then it becomes difficult for separation. And these are the data for sulfonated polyether ether ketone and MSTA incorporated. Here also I have given the comparison. You can easily see water isopropanol mixture for 10 weight% of, this is my last slide of my talk, 10 weight% of water in the feed mixture at 30 degrees. I have given only for 30 degrees here data, but however, as I forgot to tell you, this is published. You can just check it bottom. It is published in RSA Advances. You can check my paper in RSA Advances, the volume 4, 2014. This is the page number. You will get the entire picture of the whole membrane, how we modified STA. Here I cannot give everything. You can go through this paper. You will come to know how to incorporate MSTA into speak, how to modify, what are the advantages of modified speak, and what is peak. Everything it is there in RSA Advances that you can check. So if I come to data, then PV data for pristine as well as nanocomposite membranes. Pristine is only speak. Only speak separation factor is very less, 105, and flux is also very less, 0.086 kg per meter square hour. And once again, I have given STA as well as MSTA here. STA 3, 5, 7, and 10, and MSTA 3, 5, 7, and 10. Now we'll see 3, 5, 7, and 10. Here there is a difference compared to NALG membrane. The highest value, you please check there. The highest value of, first let us check STA membranes only. STA 3, 5, 7, and 10. What we are observing, STA 7 has given highest selectivity or separation factor and highest flux also. compared to 10. 10, it has once again decreased. It is very interesting here. 10 decreased, but 7 has given optimum results. Why does it happen? What happened here? STA 10, because the cesium ions increased. STA 10, because the increased content of STA blocked speak voids. That was the problem. So as 7 to 10 I went, at 10 weight percent composition of STA into speak, it however blocked speak completely. Therefore, many of the voids got stuck with STA itself. Therefore, what happened? The separation factor decreased for 10. Similarly, if we see MSTA 3, 5, 7, 10, here also we can see that MSTA 7 is giving optimum separation factor and flux compared to 10. Once again, the same problem. First of all, if we see the difference between MSTA and STA, MSTA membranes, however, once again gave fantastic results compared to STA because there was no leaching. Leaching was very, very less. But if we see MSTA 7, MSTA 7 gave highest separation factor and flux compared to 10. Once again, same problem happened here. At 10, the many of the wires themselves got stuck with MSTA and separation was lesser. At 7, we got optimum results. Therefore, at MSTA 7, we got optimum separation factor and flux. So this is the data for speak membranes. So I have talked about the basics of pervaporation, how pervaporation takes place, what is the process, and how the membranes are involved, how to modify the membranes, how to modify even the heteropolyacids, how to incorporate those acids into polymers, and how to use mixed matrix membranes into pervaporation setup, all these, and also I have provided few data of my own work. So this is how I hope this gives some idea about pervaporation and how we can use polymeric materials as membranes. That is very important. Many people think that polymeric materials, polymers are only like polyethylene and all these things. But however, we must be able to understand that polymers are used even in medicine, extensively used. Polymers are used in drug delivery. Many of the researchers have used polymers for drug delivery. Even in handiplast and all these things we use for sustained release of the drug on the skin also. All these things are possible because of polymers in engineering aspect also, scientific aspect also, and medicine aspect also. All these aspects are, however, possible. So this was my last slide. Thank you, one and all. I thank Dr. Viresh for giving me this opportunity to talk about pervaporation and polymeric membranes. Briefly, whatever I could do. I don't know whether I have made a complete justification for the whole process. But thank you, one and all.
Thank you, sir. Thank you very much, sir.
Yes, sir. Thank you. If any
Dear
questions are there,
participants, if you have any questions in your mind, you can directly ask
Sure,
Professor Sushil Adur, sir. Or
If
else
any-
you can also leave your comment in the comment box.
sure. Anything is possible, no problem. Any questions?
Dear participants, do you have any questions?
Hello. Thank you, sir. Thank you, sir. Okay. Okay, thank you. Yeah. Yes. Yeah. Correct. Yeah. Yes. 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 Yeah. Yes. Yeah. Yes. Yeah, yeah, that is important. Correct, sir. That is important. That is important for the talk. Yes, sir. Yes, sir. Yeah. Yes, sir. Yes, sir. Yes, sir. If they don't get ignited, then it becomes very pathetic. Yeah. Yeah. Yes. 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 Yeah. Yeah. Yes, yes. Yeah. Thank you. If any questions are there, welcome. Oh, sure, sure. Yes, 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 yes. Mail ID also. Yes, sir. Yes, sir. No problem. No problem. Yes, sir. Yes. Yes, sir. Thank you. Okay. Okay.
Thank you very much, sir.
Thank
Now
you.
I request Professor Shashidhar Gowda to give vote of thanks.
Hello. Hello. Good afternoon,
Hello.
everyone. Myself, Shashidhar Gowda H, Assistant Professor of Department of Physics, Tontadarya College. It's my pleasure to give the vote of thanks for the gathered participants as well as our today's speaker, Professor Sushil Adu, sir. First of all, I take this opportunity to thank our today's speaker, Professor Sushil Adur, Department of Chemistry, Ranichanam University, Belagavi, for delivering a very good informative session on polymeric materials as membranes in pervaporation separation, sir, for accepting our invitation and delivering such a wonderful informative session. Thank you once again, sir.
Thank you.
And
Yeah, yeah.
oh, sorry, sir. I thought
No, 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 it's okay. It's okay. Not a problem.
GSS College, Belagavi, sir. Okay.
Yeah, yeah, yeah. Correct, correct.
Yeah. Sorry, sir.
Yes, sir. Yes, it's okay. Not a problem.
Oh, oh,
Okay. Thank you, sir. Thank you.
okay. Thank you very much. And I also very much thankful to the organizing committee of this chemistry FDP for this particular day. That is our beloved colleague, Professor Madhu KN, for hosting this particular event for this particular day as well as particular this session. As well as I'm very much thankful to our beloved Dr. VT Magla sir, Dean R&D, for constantly guiding us for successful conduction of this particular sessions as well as this ongoing FTP. As well as I very much thankful to all our colleagues and principal, staff, non-teaching staff of Tontadarya College. Lastly, not the least, but I'm very much thankful to all the participants who have actively participated in this particular session. Thank you, one and all. A good day.
Thank you.
Thank you, sir.
Thank you. Thank you, sir. Thank you. Bye, sir. Bye.